thank you, Ricardo, to invite me to here to give a talk and to present the shortcut to Adiabaticity. Particularly, what I have been done in the University of Boston as Ramon Igahar Fellow. And so today I will talk about this issue, particularly about the shortcut for the quantum control, and also the robust, faster and robust spin control, and also digitalized quantum Diabatic, particularly to apply the shortcut to speed up the Adiabatical quantum computing. And my talk will end up with some brief conclusion and perspective on the different quantum science and the technology. So that's the whole outline. As you know that we are leaving the NISQ area, so that there will be some important issue, particularly to prepare the controlled and manipulated quantum state with high fidelity, also in a faster and robust way, with the application ranging from the quantum information, quantum simulations, and also the quantum manipulation. So that's the basic idea why we propose the shortcut. So in the quantum mechanics, you know that if we follow the state evolution, follow the slow adiabatic process, and it will give us some robust control with respect to the deviation of the system parameters fluctuation. But usually it takes a long time, so the design, the result will be completely destroyed by the environmental decoherence. So it's quite natural that we want to find the shortcut to adiabaticity, which means that we want to mimic adiabatic process, but within short time. So we want to get the adiabatic-like solution without a final excitation. So I was when the last year, almost 10 years ago, so we developed this concept in this PIL with Gonzalo Mula and other scientists. And so this field grows dramatically during the last decades. And so I would like to say shortcut, the concept of shortcut has become the front floor of the research in the quantum control. So if you are interested, you can look at the Wikipedia and also several review articles here, and also review model physics recently. And so here I just want to give you some brief idea about this shortcut to adiabaticity. For instance, we once proposed this inverse engineering based on the dynamics environment. So I will give you some examples later. And Michael Berry and Rice also proposed this transitionless driving, so all terms as the counter-Diabatic driving protocols. And also Sunpei Masuda and Nagamura proposed this fast-forward scanning approach, they from the Japan. And also Suter developed this rapid scan approach, particularly implemented in the NV center spin. And recently, the scientists from Brazil, they developed this time scaling dynamics, and also the Takahashi in Japan, they also developed the Lux pair from the classical and linear integral system, from the classical to quantum. Of course, the shortcut may also share the concept to speed up the adiabatic process, and also it could be include some techniques about this optimal control theory, and also enhance the shortcut developed recently by the NLS. So I would like to say that this kind of the techniques share this same concept, the motivation, but for the different system or for the different physical constraints setups, you may choose one of them or combine the different shortcuts together. For instance, we can combine the inverse engineering with optimal control theory to achieve the faster and robust quantum control in the trapped ion in the atomic systems, for instance. So here I just want to give you the basic idea how we design the shortcut based on the dynamics environment and the counter-Diabatic driving. This is the two most the popular or the important techniques for the shortcut. Okay, the idea was like that. So basically, if you have the time-dependent Hamiltonian, then you can find the dynamics environment based on the sum D algebra. And then based on this condition, di divided by dt equals to 0, then you can have these conditions, and you can write down the solution of the time-dependent shifting equation based on the dynamics mode of the environment. So this is normally the Lewis theory give us the solution of time-dependent shifting equation. But here, we just want to use these things for designing the shortcut. For instance, we compose these commutators at the initial and the final point, such means that our state evolution will consistent or coincide with the eigenstate of Hamiltonian at the initial and the final point. And with these conditions, so that means the initial and the final state are guaranteed to have the coincide the eigenstate at the initial and the point. This gives us the shortcut to adiabaticity for the systems with the Hamiltonian edge when we can find the dynamics environment. Okay, so then there's another simple shortcut, the second method we call the counter-diabatic driving, or microbarriers called transitionless quantum driving. And we extend these things from to the two-level system and the three-level system for the atomic system. And the idea is very simple. So for instance, when we want to transfer the bottle of the water in the clouded environment or the restaurant, we want to avoid the spoiled water. So how to do that in the crowded restaurant? So we can add some force, compensating force, to prevent this water spread out of the water. So physically, so we call this the diabatic gauge potential, which is responsible for the transition. So if we look at this, the Hamiltonian in the instantaneous eigenstate basis. So if we add the CD term, which means that we add this term to suppress the diabatic transition in the Hamiltonian, which will means that the total state evolution of this Hamiltonian will mimic the adiabatic evolution of this original Hamiltonian by adding the CD term to avoid the excitation. So this has the problem. For instance, in some cases, it's hard to implement in the lab. One has to find the effective or unitary transformation to do that. And on the other hand, if we look at the Hamiltonian, then we need the prior knowledge of the system eigenvalue. Then people's work in the in the many-body system, they may say, okay, it's useless. For instance, if you can calculate the eigenstate, then you solve the problem. Why you need the CD term? Then with these two papers, people stand these things a bit more. For instance, they use the concept of local CD term. For instance, they only assume the sigma y terms and leave the freed parameters alpha j. Then they want to minimize these actions to find the coefficients alpha j, and then they can find the approximate local CD term in this way. Somehow they can extend from the single particle to the many spin. I will show you the later. And from the concept of the Foucaultian engineering, they use the nested commutators and they design the approximate gauge potential in this way. And for the first order nested commutator, and it becomes very simple. And this coefficient, when we obtained, then we can write on the CD term for this approximate gauge potential. So this gives us the freedom and the extension from the single particle to the many-body system. And I will use these things for later to speed up adiabatical quantum computing later. Okay, so here I just give you the two basic idea how we design the shortcut based on environment, based on the CD term. And this field scrolls up because of different experiment progress. Here I want to mention the global picture, which is dedicated to the experiment achievement. For instance, the experimental group in France, they implement the shortcut in the composition of the cold atoms. Georges Meyer did it for the Guasa condenser, and Weiland used the shortcut for the trapped ion, the transport or the splitting. And Haibing Wu in China, they do the Fermi gas expansions, also developed the things for the quantum heat engine. And King in Tsinghua University, they also do with Adolphe, of course, do the trapped ion in phase space with the shortcut. So, and of course, people are also are interesting for the internal state control for, let's say, the 2-level system and the 3-level system for the quantum information processing. And in Oliver, they developed this 2-level system in the accelerated optical lattice. They use the CD term to speed up to achieve the high fidelity driving. And for the MV center or the superconducting qubit, and they did a lot of things. I also collaborated some Chinese group. We developed this speed up acceleration of the stirrup with the cold atoms. Somehow we added the CD term after the unitary transformation. We can speed up the conventional stirrup and to achieve the high fidelity control with the atoms. And also people are doing something for the spin chain. And also why this field becomes interesting, because we can also go beyond to the quantum technology or the quantum system. And I just mentioned a few works here. For instance, David and other scientists in France, they extend the shortcut to the statistic physics, also even in the biology. And I would like to also mention, because here people are also interested in the nanoscience, also low dynamic system. For instance, people can also use the shortcut to achieve or switch the fast equivalent state in the nano mechanical oscillators. And of course, in the classical system, in the RC current, CRAM, also optical waveguide, also the optical polarization, we can get the effective 2-level system or the harmonic oscillators. Then we can use the shortcut techniques to engineering the differential equation and to design the shortcut for the classical systems as well. So that's the global picture. Here I want to focus on what I did during these 2 years. And we developed the shortcut for the cold atoms and also spin system and quantum computing. I will give you the details. For instance, let's start from a very beginning model. For instance, we have the time-dependent harmonic oscillator. This is a time-dependent trap frequency, which will be interesting for cooling down the atoms in the optical dipole trap. And then for this Hamiltonian, it's very easy for the theoretical physics. It's easy, and you can find the dynamics environment in this way. With this dynamics environment, the condition di divided by dt give us the very famous Markov equation. And originally, you know that if we substitute the time-dependent frequency like the quench protocol, then you can solve this differential equation. With this dynamics mode, substitute this B, and you will get the solution of time-dependent Schrödinger equation. But here we did in opposite way. For instance, why we don't design the B first and substitute B with some boundary condition, and we can interpret the B and to design the trap frequency later. This is what we call the inverse engineering. And then we can generalize this single particle to the gross Adiabatic equation for the boson condensation with the interaction include. And look at this equation, then with this self-symmetric dynamics, we will have the similar Markov equation. But we need some condition. For instance, we need for one dimension, the GP equation, we need a time-dependent G. For instance, to get a similar Markov equation, G should be equals to G0 divided by B. And on the other hand, to make this self-symmetricity valid, so we need the Thomas Fermi limit, which means that this interaction goes to infinity, and we can completely ignore the kinetic energy. Then we get the modified Markov equation. So this gives us how to design the shortcut for atomic cooling. So we have the Markov equation and this modified Markov equation, which working for the non-interaction case or the Thomas-Fermi limit. So that's the logic. Then how to generalize these things to go beyond these two cases. And we want to study the cases of the weak interaction, except for the G equals to 0 and the G goes to the infinity, as I mentioned. So we look at the variational approach, approximate approach for the shortcut. So we can get the longer density, and we can choose the Gaussian ansatz, substitute these things from, then we have this Euler-Lagrange equations. Then finally, we get the similar Markov equation, but the interactions is included. So this gives us the possibility to design the shortcut by taking into account the nonlinear interaction. That's very interesting things. And also with this work, Huang in Sisek, they noticed that these things can be designed shortcut for the arbitrary potential. For instance, in the superconducting qubit, there will be the unharmoniously part potential. Then somehow using this variational approach, then they can design this frequency tunable transform qubit control by using this variational method. So that will be very nice. So of course, as I said, that we can also combine this variational approach with optimal control. So I just give one example. For instance, we can calculate this time optimal control problem, because this minimal time minimal problems will be interesting for different respects. For instance, this will be relevant to the quantum speed limit, which is also interesting fundamentally. The other thing is that this cooling process is also relevant to the compression or decompression of the atoms in the quantum heat engine on the quantum refrigerator. So this is interesting for the quantum thermodynamics. For instance, look at these figures. We calculated this is a very simple mathematics. Finally, we can get the minimal time for the different cases, because as I said, that this variational method allowed us to calculate the minimal time and the shortcut with different interactions. So look at this scaling. This is the minimal time with respect to the log f omega frequency f. This means that this is the final frequency of the trap. If final frequency trap goes to the 0, which means that we are in request of absolute 0 temperature. So in principle, based on this third law of the thermodynamics, which means that this TF goes to the infinity. But we will look at different exponential scaling in the different cases. For instance, look at this Thomas-Fermi limit, which means that G goes to the infinity. This scaling will give different with respect to the different interaction. So this will give us the different cooling rate when we consider the atoms as the working media in the quantum refrigerator. So look at these things, and this you see for this expression gives the 1 minus the 1/2, and this is the third divided by 2, and with this is for the non-interaction, this is for the interaction. So this scaling gives us the different cooling rate. That's why this is interesting for the different things, particularly fundamental for the quantum thermodynamics. And that's why this also motivated us to use the soliton compressions in the quantum heat engine. So we just simply change the ansatz for the bright soliton, and this is similar to the previous Markov equation. Then we can design the shortcut. But here we look at using the metal wave solitons as the working medium, and we can calculate this quantum heat engine by compressions and also decompression the protocol with the shortcut. So you will see that, okay, with the shortcut, you can really see how when we shorten the operation times, the power increase and the efficiency also increase. And on the other hand, we also look at the interactions, how interaction affect this efficiency and the power. You see that the stronger interactions will give us the better overall the performance. On the other hand, you see that there's a peak in the power, which means that your shortcut times will not be the infinitive short. Why? Because when you shorten time during the intermediate steps, atoms will be excited in any case. So then it will make our method broken down, and the atoms will escape when you have some environment, also the anharmonicity. That's why this shortcut broke down at a certain short time. That's the basic idea. Of course, when we use the Fischer-Blacher resonance to control the atomic system, and usually we have the Bang-Bang control, and we need to control the interaction through the Fischer-Blacher resonance, and it will go from the negative to positive the interaction. And when we cross the zero, and it will induce some atoms loss. So that's why here we use the small regularizations to smooth the Bang-Bang control. And here we compare how the minimal times affect, and also we do the simulation for the 1D and 3D, the Bose-Einstein condensation, to see how it affected for instance, for the fidelity and also for the minimal time here. So that's the basic idea. As I said, that Huang Hao also noticed that this variational method can be generalized to the arbitrary potential, which can be useful in different setup, for instance, the optical lattice and the superconducting qubit and other things. Here, we just want to look at the power law potential. Why we are interested in it? Because we are not only considering the atoms, but also talk about the spin polarization Fermi gas, also the Tok's gas. So look at these figures. If we want to keep the atoms stay at the original instantaneous eigenstate for the TG gas or for the spin polarization Fermi gas, usually we want to keep the excited state stable. And because of this Pauli exclusion principle, then we can predict the other state below this excited state. Then with this motivation, that's why we can assume the excitation, any excited state as the ansatz instead of the ground state Gaussian ansatz. And meanwhile, we can modify this power law potential. Then we can get more general solution here. And just to give one example for the quadratic potentials, then we can simplify these equations, which looks like a similar Markov equation, but with different coefficients. And then you can look at this by using the ground state as ansatz or the excitation ansatz, and you will get the different fidelity, right? And then here we just consider the 15 as the particle numbers. Okay. So why, as I said, that why we are interested in this, because we want to look at the Tok's gas and also the polarization Fermi gas. Because for designing the shortcut for this gas, extremely cold gas, then for the fidelity, you don't look at the difference. The fidelity will be the same because of the both Fermi mapping. But TG gas and polarization Fermi gas will have different coherence. Look at this reduced single particle density matrix. This is for the Fermi gas. This is for the TG gas. And you look at these things, and the coherence will be different. So we are also look at the eigenvalues of this reduced single particle density matrix. You will see the difference. For instance, this Fermi gas is proportional 1, and the TG gas is proportional to the square n, which means that the coherence of this TG gas and the Fermi gas will be different. So that's why we further look at this velocity and also the quantum speed limit. This is the trace distance. Look at these figures, and this we define this as the velocity. and look at this difference. And the velocity for the TG gas and the FEMI gas will be different, which means that the coherence plays an important role, and the TG gas usually is faster than the FEMI gas. That's the logical. That's why. But as I said, that if you just design the shortcut for both things and look at the fidelity, the fidelity for these things are totally the same. That's why we use this quantum speed limit in the platform of shortcut, and to clarify the difference influenced by the coherence. Okay. So recently, I just go beyond a bit, because we can also choose the hydrodynamics equation instead of Gaussian answer as a high excited state. Then we can use this more general transformation, and we can get the more general solution, because A and B and different. But A plus B equals to 1, sorry. And then we can get the more general solution. This allowed us to connecting from the non-interaction case and to the strong interaction cases. Then look at this fidelity for the shortcut. You will see that this Markov equation gave us more accuracy description of the dynamics for designing the shortcut. That's the only message that I want to tell you. And if you are interested, you can look at the papers in details. And then just now I look at this harmonic trap. It's almost relevant to the orbital motion control. Here I want to also mention some spin control, let's say the internal state. This is much simple. I want to give a very intuitive picture. So this is the spin rotation on broad sphere. So if this is the isomersal angle and the Pauling angles. For instance, for the spin evolution, we can design the trajectory both based on these two angles. Then we can design or inverse engineering the magnetic field to flip the spin. That's very simple. So this is the shortcut. So we can give you the state evolution. Theta is just from the 0 to pi or pi to 0. This is spin flip. To make it non-trivial, so we just assume very simple polynomial answers for interpret these functions. And then we can easily to get this shortcut for the spin flip from the 0, 1 to the 1, 0 to the 0, 1. And we can design this electric field through the tunable spin optic coupling to design the spin control in the quantum dots. So that's the very simple idea for the single spin. For the two spin with the interaction, we look at the Ising interaction, also Heisenberg interaction. For the Ising model, look at the spectrum, then there appear the avoided crossing things, and then we can get the effective two-level system around this point. This is avoided crossings. Then basically we can consider it as the effective two-level system, but with some modification. For instance, we look at this two spin. For the three spin, we can generalize this effective two-level system just by modifying the square n. For instance, this is for two-level system. For two spin, this is square 2. For the n spin, this is just the square n. But one has to be careful to look at the spectrum at a certain point to guarantee that this is the avoided crossing. So then we can do that. And with two-level system, we almost solve the problem. And then we have the theta dot to parameterize the state evolution. And then we can use the simple answers to interpret this function. But as I said, that we can always combine the shortcut with optimal control. Then we can say that if we put some noise in the magnetic field, how to design the optimal robust shortcut. So we can put the answers, and by using time perturbation theory, then we can get this so-called noise sensitivity or the error sensitivity. And very surprisingly, for the error in the magnetic field, we can get an analytical solution. So this theta, we just simple some answers to interpret the boundary condition from 0 to pi. And then with this error sensitivity, this is just the transition induced by the error in the magnetic field. Then we can, by using the Euler-Lagrange equations, we can get the optimal solution for this theta and beta. Then you can design the magnetic field and the detuning and get the extremely, not extremely, at least the optimal shortcut with respect to the arrow in the magnetic field. This gave us the concept how we combine the shortcut with the optimal control theory to design the shortcut for the two interaction the spin. As I said, that we can also generate to the mini spin. And here we compare the composite process with this shortcut. For instance, we just choose a very simple X, Y, X composite process. You will see that this infinity shortcut is always better, of course, than the resonance pi path and the composite process, just because of this estimated the exponential fidelity for exponential behavior. For instance, this infidelity proportional to delta square, delta to 4 for the composite process. This is for the pi path. It's quite few. What I want to say is that it's not good enough. Then we compare this shortcut with composite process. Then we got the idea why we don't insert our shortcut process into the composite process. For instance, in Horrocks papers, they are also doing some hydrogen, for the quantum sensing. They usually use the pi XY8 composite process, like XY process consequence. And then we were thinking that why we don't replace the resonance process by the shortcut process and to see how it behaves. Then we look at these figures. Then we design the shortcut by the previous method, as I said that in the previous slides. And then we insert the shortcut in the XY process. And we get the extremely good result for the quantum sensing and for especially for detect the robust detection of the high frequency signal in the MV center. Of course, we have also did it for the stirrup. For instance, for the stirrup composite process, this is the normal one. Then we can insert our optimal shortcut in the composite process. We will get the different result. So this will be also interesting to develop the quantum sensing later. Also to the neutrino spin polarization in the MV center, we can apply this method to that. And as I said that, we always want to generalize this shortcut from the two-level system to the multiple-level system. Here, I just give you 3 examples. For instance, in the double quantum dots, we look at this double quantum dots, then if we have the effective 4-level system, and by using the double rotation, somehow we can parameterize the state evolution, as I always mentioned before. Then you can get the state evolution and to design the shortcut. Then we can get the arbitrary spin control. For instance, here we just give an example. We want to achieve from the spin level 1 to the superposition between the 2 and 3. And we want to control the spin orbit coupling. And then we can design the spin coupling based on the inverse engineering, and we can achieve the fast shortcut. And here I also working with Yuan and also with Gloria Bladero, and we want to use the shortcut for the charge qubit control and also the entanglement state control in the quantum dots area. For instance, here we want to transfer the charge qubit from the left to the right. And as I said that for this state, because of some Lie algebra, the symmetrical property, finally we can get an effective two-level system just by modifying the original Rabi frequency. This is just the square n because we consider the n quantum dots area. Then with this two-level system, then we solve the problem as usual. So we can transfer the state from the left to right and to in the arbitrary robust and fast way. Of course, we can also consider the entanglement state in the in quantum dots area. Then we can transfer the entanglement state from the left quantum dots to the right quantum dots, and we can have the similar result for the spin entangled state. So people will always ask, the shortcut is relevant to the optimal control, relevant to the component process, also whether this result is consistent with the machine learning. So now last year, I also tracked how this shortcut result is consistent with the result from the reinforced machine learning. So I developed these things with my students and also colleagues. So we just think that, okay, we want to get the robust detuning for the single spin rotation. Very simple. And we know that the shortcut result, as I mentioned before, and we also know the result about the resonance bypass. So can we use the deeper reinforced learning to train the system to get the faster and robust control for the single spin qubit? Yes, because it's relevant to the spin rotation, it can be useful for the digitalize the quantum circuit. So that's why we start to develop. Of course, as I mentioned that, here we just add this systematic error, just wanted to compare our previous result. Of course, you can also include some environment noise. Here, I want to emphasize we didn't include any statistic noise. We just put the systematic error and to train to give the constant the reward, and we have the agenda and to have this result. Here, I want to emphasize the three things. First thing is that deep reinforcement learning give us the similar behavior, but it's a digital shortcut process. Look at for the shortcut process, the previous protocol looks smooth, but here it looks like the digital process. The other thing is that, okay, look at, because we didn't consider any statistical noise, the result is very easily to adapt to the bypass. Because why? In the whole world, bypass is the fast one. So if you training this deep reinforcement learning, then you will get easily to converge the bypass. So then I would like to say, if you want to get a robust the protocol, so you will find the middle point between the adiabatic process and the bypass. Then the shortcut educated the reinforcement agent will to give us the result, the robust behaviors. So on the other hand, deep machine learning will expose the different things. For instance, we add a different noise and perturbation, which shortcut cannot handle. And then similar things, deep machine learning will also give us some result. Of course, we are also collaborating with the experiment group in China. They also did the experiment with the trapped ion system in Hefei. And of course, we did several things. Here, I want to speed up a bit, but I just want to give you the global picture how this shortcut works for the mini system. For instance, we also look at the nlinear two-level system. In the many-body systems, for instance, for the nlinear GP equation, and we want to transfer the Bose-Einstein condensation from the left wire to the right wires. And with interactions, you will have similar curve nlinear interaction. And it's interesting because of the Bose-Einstein condensation in double wire, also bosonic US function junction. There are a lot of work in Barcelona, for instance. And also this is received the Hamiltonian in the nlinear coupled waveguide. And then another thing is another type of the two-level system is more complicated, but it's interesting. People are also use the Fischer-Wahrhahn resonance to prepare the molecular BEC from the single atom BEC. And then you will have this more complicated nlinear two-level system. Apart from the current nlinearity, you will have the other three-order non-interaction. Then we use the paragliding maximal principle. We calculate the minimal time for this Hamiltonian and for this Hamiltonian. And there are several things for this nonlinear system. It's much simple. You can use the high driving high driving in the detuning and to compensate the nonlinear. Then in nonlinear interactions, then you can get the bound control and the bound shift the bound control. Of course, if nonlinear increase dramatically, then the system becomes chaotic, and you cannot transfer the state, and the state just rotated here become the chaotic property. And for this Hamiltonian, we will get the Joffit Broch sphere, effective Broch sphere. Then we can always get this shortcut optimal control problem. And here I just want to give you several ideas. For this special nonlinear system, one cannot achieve the population transfer within the finite time, because you can see that this is a tangent, hypotenuse tangent, and once the t goes to infinity, then you will get the approximate one. Otherwise, you will not get the perfect one, which means that in this system, you don't have a population transfer with a finite time. On the other hand, one can get the quantum speed limit for this system because we calculated the minimum time, and you will see that this minimum time doesn't depend on the driving. For instance, the tuning here, and you will this minimum time only depends on the initial and final state with the coupling as well. So that's the basic idea. And as I said that, I always say that, okay, the shortcut can be complemented by the optimal control problem. But for this nonlinear system, you don't have any analytic optimal solution. But we can always parameterize the state evolution in this way, such that we can get the Hamiltonian based on these two parameterize the angles on the effective Broch sphere. Then once we choose the theta and alpha on this Broch sphere, then we can design the detuning and the Rabi frequency for this more complicated system. Why we are interested in, I just want to mention these things because for instance, when we want to control the state from the north pole, source pole to the north pole, because of these nonlinear interactions, and usually the result is not stable at all. It will be sensitive to the parameters fluctuation, sorry, and then it's quite demanding for us to design the faster protocol, of course, meanwhile to get the robust stable control. That's why here we search the parameters to get the better theta and the gamma for the control. Then we can design the fidelity, also the protocol. This is what we did, and of course we can also generalize these things to the three-level system as well. Okay, so just now I talked about the harmonic oscillator, orbital motion, and also the internal state. Then people in the audience will ask, oh, how about the shortcut with spin-orbit coupling? It's quite natural, so we are working on that. Very interesting. I just nowadays, you know, the flying qubit in the quantum dots with tunable spin-orbit coupling, and you will also know that there's a lot of experiment achievement about this spin-orbit coupling boson in the condensation. Then we can look at the very simple example. First, we just completely ignore this interaction, of course. But we want to design the shortcut. Let's see, we want to move the boson condensation from 0 to D, and meanwhile to flip the spin by adjusting or designing the coupling. This is the spin-orbit coupling. And with the similar idea, because of this Hamiltonian, it's very easy to solve analytically because we can write down the unitary transformation based on this equation. And with interaction, we cannot do that. Okay, but without the interaction, we can solve this equation analytically. And once we solve this analytical equation, somehow we can connect the Hamiltonian H0 and also spin-orbit coupling strength with the state evolution XC and alpha C. XC is relevant to the position of the wave function, and alpha C is relevant to the spin rotation. And then, because of spin-orbit coupling, then you will see that this spin-orbit coupling is coupling to the orbital motion. somehow it makes sense. And with these three equations, somehow we can set the bound condition for the hxc to the 0 and also alpha c, because we can, for instance, if we want to flip the spin, then we can put the bound condition for the phi from the 0 to pi over 2, then we can, then the state evolution will be guaranteed with the spin flip. Then we can design this protocol function and see the numerical simulation. We transfer the VC with the spin flip, sorry. Then, of course, we are also applying these things to the spin readout for the circuit, quantum superconducting circuit, sorry, and also the quantum dots. That will be interesting for further exploration. And okay, so the last part I want to emphasize that nowadays people are also interested about this adiabatic quantum computing. So now I'm working on the adiabatic things or the shortcut to adiabaticity. Just here, I just want to give you some basic idea about this adiabatic quantum computing. I took these sentences from this review article written by the leader. So basically, you can have this Hamiltonian. So if lambda changes from the 0 to 1, then you will end up with the final state of this problem Hamiltonian. So I will say that, okay, so the adiabatic quantum computing will give us the solution to find the final state of this problem Hamiltonian. In principle, any computation problem can be encoded in this way. And of course, because we mentioned this adiabatic quantum computing, it's quite natural that the running time depends on the minimal energy gap. Let's see. So the time should be 1 over by the energy gap. So and with this famous paper in the Google, and people also mentioned the things that they can implement this digitalized adiabatic quantum computing. The idea that one can write on the time evolution operator in this way by using the total steppers. One can digitalize these time evolutions, and then they can implement the different total steps and to get to the final solution. And here, I just want to make the question for myself. For instance, we have looked at the shortcut, for instance, the inverse engineering or the counter-diabatic driving. The intuitive idea is that if we have the circuit, digitalize the circuit, if we insert the counter-diabatic driving, borrows the idea from the shortcut, what will happen? That's the basic idea. So that means that we want to propose this digitalized counter-diabatic quantum computing to see that whether this counter-diabatic driving can help the quantum computing, particularly to get the faster and robust result with the shallow circuit depths. That's the basic idea. So why? Because the counter-diabatic driving will force the state to state the instantaneous eigenstate during the process. That's what I mentioned when I introduced the concept of the shortcut, particularly for the CD term. And yes, I just want to give the simple example here. Start from the simple example. For instance, we have a single spin, which is easy. So we can sigma x and sigma z. So we just want to rotate the spin, and this lambda goes from 1 to 0. Here we just assume the sine function and the sine square function. Then with this Hamiltonian, one can apply the counter-diabatic driving mentioned several slides ago before. Then we can calculate the CD term. This is nothing but a sigma y term. You can imagine that, for instance, on the Bruce sphere, you want to flip the spin. How to speed up it? Because when you speed up a spin starts to the processing, become not follow the magnetic field because of the adiabatic transition. Then one add the sigma y term to force the spin follow the magnetic field. That's why the CD term plays low. This gives you the intuitive picture of the counter-diabatic drive. Then we can digitalize this protocol and put in the acoustic and to calculate it. That's very easy. So we will get the result. The only point is that, okay, with the CD term, we can achieve the result within the short time. And meanwhile, when we include some noise in the acoustic, then we will get some good result at a certain point. And that's motivated us to do more things about these things. So for instance, we can look at the two interaction spin to prepare the bare entangled state. We still get the better result by including the CD term. And then with this method, some people in Hefei, they immediately say that, okay, this digitalized counter-diabatic driving will be useful for the VQE, variational eigensolver. And then they insert the CD term in the circuit and try to speed up to finding the ground state of molecular. And they do some results and look at this digital shortcut performance, and you will see that, okay, for the original protocol, you need more steps, but within shortcut, then you can achieve the exact fidelity just with a few steps. That's really quite something. For instance, in the noise in the circuit, if you can shorten the circuit depth to find the ground state, that will be fantastic, and it will also help us to achieve the quantum advantage with small circuit depth and also less complexity. That's quite interesting. That's why we developed these things further. Now, I would like to say that we almost concentrate these things during this month. So we look at the easing model and to prepare the GHZ entangled state by using the nested commutator. I mentioned several slides. Okay, then we will see that, okay, for the large spin without CD term and the fidelity decrease, but with high order nested commutator, somehow we can improve the fidelity by adding the counter-diabatic driving here. And also we look at the different things, for instance, using the local CD term, and the behavior was not good. When we increase the interaction here, and the fidelity is not good. Anyway, so then we can move to the other counter-diabatic driving, this nested commutator, to improve that, even to keep high order nested commutator. But in any case, up to some certain point numbers of qubits, we will still get some result. And this is just the direct application of the counter-diabatic driving based on the nested commutator, also the local CD term. And later, we are combining the circuit learning to do things. That's why we extended to a lot. Recently, we published the 3 papers, some accepted in PRA, some in the archive. So we really appreciate the role of the CD term in the different things. For instance, we want to add the CD term to speed up the adiabatic factorization. And in these papers, we separated the 2 problems. For naively, we have this problem, then we can write on the Hamiltonian by introduce this poly matrix. Then you will include the 2-body, 3-body interaction. For factorize the larger number, it will not work. So we combine the multiplication and also classical processing, and to get effective Hamiltonian, which only include the 2-body interaction. Then we add the counter-diabatic driving. Then we really see that implemented in the acoustic, of course, and we will really see that, okay, the CD10 can speed up the adiabatic factorization, and we see the better result. And of course, the QAOA is also the very standard or popular method, hybrid classical and quantum algorithm. Nowadays, it's very interesting for the optimization problem, also classical optimization like the max cut problem. And usually for the QAOA, then people use the P layers. And here we want to include the 3P by adding the CD term here. Then we use the classical optimizing to see that whether we get the better result of the conventional QAOA algorithm. Then we in these papers, if you are interested, you can check the details. So in these cases, we look at the longitudinal Ising model and the transversal Ising model, and to prepare the DHC state. Also, we look at the SK model and to look at the classical max cut problem. And here, as I said, that so for instance, in some cases, the local CD term doesn't work perfectly. Then we need the classical things and to optimize the coefficient of the CD term. And with that techniques, we really improved a lot. Then we can apply it to the financial model and by using the similar idea. And recently, we also look at the more general QUBO, this quadratic, the unconstrained binary optimization problem. Here, you will see the advantage of the shortcut. Here, what I want to mention is that why in these figures we clarified why this CD term will help the adiabatical quantum computing here. Look at these things. We calculated the energy gaps and look at a certain point, the CD term somehow increased the energy gap at a certain point. That's why it helped us to speed up the adiabatic quantum computing. Meanwhile, we will also consider the CD term as the non-statistical catalyst because normally people can working on this catalyst list to speed up the process by including the two-body interaction. But here, we really consider that this CD term is non-stochastic, and it will also help to speed up the adiabatic quantum computing. This is the application with this shortcut we call the quantum control inspired the quantum algorithm. This is we are still finding a new application, for instance, different application, let's see. So here, so I would like to conclusion a bit. So here I start from the original problem to cool down the atoms in time-dependent the harmonic charts. And later we go beyond to that because this time-dependent harmonic oscillator will be interesting for the different respect. For instance, superconducting, optical lattice, also in the electric in the surface acoustic wave, for instance. That's why we want to go beyond to the high excited state, also to the more arbitrary potential. This is what we did for the first part. Later, we are more focused on the internal state. Let's see, control the spin, because this spin is relevant to the MV center, trapped ion, also the spin in the quantum dots, and we can generalize from the single spin to the mini spin. And of course, recently, I'm also interested with this nonlinear system, particularly to transition or the state transfer in the atomic and also molecular Bose-Einstein condensation by the tunable Fischer-Barre resonance. And meanwhile, I'm also keeping in mind because recently people are interested in the quantum algorithm, then why we don't use the concept of shortcut to speed up the adiabatic quantum computing. And here I just tried one of the concept of shortcut, for instance, the counter-diabatic driving. Of course, I'm also thinking how to apply the optimal control, also the fast forward to speed up the algorithm. There's a lot of to do that. And meanwhile, nowadays people are interested in the classical machine learning. So I'm also using the supervisor learning for the quantum control, particularly in the random potential. Let's see the random noise. And as I said that, I'm doing the quantum control inspired algorithm with this shortcut concept. Let's see how to achieve the quantum advantage with shorter circuit depths. And also with this different potential, we are also doing some splitting of the atoms, and particularly with the application in the quantum interferometers or the modulator. And we will see how to do the fast splitting. Because we are using the dynamics environment, somehow we can merge these two arms and to get the interference and to see how to improve the sensitivity for the atomic physics. And we want to really see something about the quantum sensing and the interferometer with the outer atom. This is what I want to explore later. And here is the collaboration. I just want to mention the colleagues in the University of Basque Country and some colleagues internationally, and some groups in Bilbao. And thank you for the funding from the Ministry of Spain. And thank you for your listening. That's all.
Questions, comments, remarks? I actually have a question. So when you mentioned the flipping of the spin at an arbitrary speed, and then you also do it for 2 spins, do you mean that you can do quantum gates as fast as you?
Yes. I didn't do that, but there are a lot of work dedicated to the quantum gate. So basically, you can write on the unitary in terms of these 2 angles. Then you fix the boundary conditions, and you can design the quantum gates for by using the shortcut. There are several work. Essentially, when I mentioned this experimental progress for the in MV Center, some groups they do the non-adiabatic homography quantum gates by using shortcut in MV Center.
And
several work.
And what about the errors? Because I guess that if you can do quantum gates so fast, maybe they are more sensitive to errors, let's say, or in practice, I mean.
Okay, this is a very, very interesting question. So that's why when I give a talk, I always emphasize that shortcut will not give you all the things in free. You are right. Essentially, so Adiabatic is a robust one, and PyPass is a fast one, but not robust with specific things. And it seems that shortcut will always give you the intermediate point to consider different respects. That's why when you say that, okay, when you speed up these things, you may lost the robustness, or it depends on your request. You see the point.
Okay.
Yeah. There's always in the middle point. For instance, when you consider, just to give you a very simple example. For instance, when you consider the diffusing noise, and you will say PyPass is the best one because it's fast. But if you consider systematic error in the Rabi frequency or detuning, then you need to manipulate the Rabi frequency and the detuning a bit, no matter you use a shortcut or optimal control. Then if you consider all these constraints, then you will find the middle point. Then I will say this freedom gives us the work to do.
Okay.
I think it's clear. Huh?
Comments? Oh, I actually have another question. So can you speed up QAOA then using this content? And how much is the speed up? I mean,
in which sense?
I don't know, for a typical.
Okay. We are fighting with work, but at least I will say that for the similar problem. Normally for QAOA, we have 2p equals to 6, and by include the CD terms, and we have the 3p equals to 3, which means that original you need a p equals to 3, and now we have the p1, something like that. I just want to give you the intuitive picture like that.
That's
of course, as I said, that there are some difficulty.
Yeah.
For instance, when we have a larger interaction or whatever, normally the local CD term doesn't work too much. That's why now we want to combine the classical optimizer. Even some papers in Princeton, or I didn't remember the author, they applied this reinforcement machine learning to optimize the coefficient of the CD term. And maybe it works better. So that's why we are still exploring that in this direction. But here, as I said, that I just using the original coefficient calculated by the Michael Berry and others, and to get this C. Yeah.
Good. Excellent. Okay. So questions, comments? No. Okay. So oh yeah, you have a question.
So you say you can accelerate the adiabatic quantum computing, but I'm not. It's not clear for me that which kind of price you should pay.
Good question. Good question. When we did the first papers in physically applied to accelerate this state preparation for the 2-spin, 1-spin, then normally, as I said, that when you speed up, you will always increase the pauses to pay the price. But when we implement in the acoustic, we didn't see this kind of constraints. So somehow we shorten the time and we add the CD term. At least I would say when we implement in the acoustic, they didn't alarm that we go beyond the limit of the pulse amplitude or something like that. This is what I can think. Of course, one can go to the details. For instance, there are always some difficult fundamental questions. For instance, when we use the adiabatic things, we can always compare the errors induced by the total steps or the adiabaticity, and to calculate the details of the cost of the shortcut. This is what we can do fundamentally.
Okay.
Practically, so we didn't see anything. Fundamentally, yes, there's a question like that.
Okay. Okay. So comments, questions? Okay, so yeah, thanks a lot.
Thanks a lot. Yeah.
Thanks for the speaker again. And yeah, I guess we will be around for the rest of the day. So if somebody wants to keep, feel free. Yeah. It's cold. It's very cold. Most like a hold up.
Cool down.
Yeah, we are cooled down to the ground state. Yeah, nice talk. So you are now having lunch with Ricardo.
Yes, and now he is running to the radio.
Oh, okay.
And we can meet.
And then you meet afterwards. Oh, that's fine. Yeah, no, because I cannot stay because I have to go. But yeah, why nice having you around. Okay.
Okay.
Yeah, no, perfect. So yeah, enjoy the rest of the day. Okay.
Yeah,
and if you want to chat or discuss about anything at some point, just send me an email if you want.
Okay. Then we can start to collaborate. Or
yeah, we can. Yeah. I think
it's very interesting. I didn't say too much, but I would like to say that okay. So with this shortcut, so we made some experts about this.
Yeah, no. I mean, there are lots of things.
Frankly speaking, I didn't say, but somehow so far I think it's too bad to be too good to be.
To be true, yeah.
So I think there's some mysterious things there.
Then probably it's too good to be true.
Yeah, that's why I assure you that I want to let the student to calculate this energy spectrum to understand why this shortcut works. Because you look at this state evolution, then we just need a very short circuit depth. For the adiabatic things, maybe you need 4 or 5, even 20 total steps. But within shortcut, you only 2, 1.
Yeah.
Too good to be.